Hello, welcome back. We are working on our ninth installment of Chapter 16, and today we're going to talk about figuring out the pH of solutions of salts, so ionic species dissolved in water, and these are species that contain a weak acid or a weak base. Sorry, we already did that one. We are today talking about species that contain a weak acid and a weak base. So like before, I'm going to work through examples. And our first example is, do you expect a solution of ammonium formate, NH4CHO2, to be acidic, basic, or neutral? So again, in our first step, we dissolve the salt in water. And so when we put an ionic species, a solid, in water, it breaks up into its ions. Now, ammonium, this is ammonium formate. It can be a little tricky to figure out which ones are their ions, but I believe that as you use the Ka-Kb table and become more familiar with these, you can start seeing some of the patterns. And so this salt is made up of the ammonium ion and the formate ion. And so whenever the salt dissolves in water, it breaks up into the NH4 plus, the ammonium ion, and the CHO2 minus, the formate ion. Now, the second step is investigating the cation reaction with water. And so in this case, in this case, ammonium, our NH4 plus ion, is our cation. Reacting with water, this is our acid. So base takes the proton, leaving us with NH3 plus H3O plus. This is a weak acid reaction. And so it has a Ka value. Now, remember, our NH4 plus is not on our table, and so we have to do Kw divided by Kb, which is 1 times 10 to the minus 14. And I'm looking up the Kb of the ammonium ion, so I find the Kb for this guy in the table, and it is 1.76 times 10 to the minus 5, which is equal to 5.68 times 10 to the minus 10. Now, we have to do the same thing with the anion reaction with water. And so the anion in this case is the formate ion plus water, forms an equilibrium with formic acid and hydroxide, because this is the base, water is behaving as the acid. This is a weak base, and so the reaction can be described by a Kb that equals Kw over Ka, which is 1 times 10 to the minus 14, and the Ka of formic acid, I'm using my table right now, is 1.8 times 10 to the minus 4. And so I get 5.56 6 times 10 to the minus 11. Okay, so now I have to put it all together. So now, when this salt is dissolved in water, I get NH4 plus in solution is a weak acid. The formate ion, CHO2 minus, is a weak base. That means that the ammonium is producing H3O plus, and the formate is producing OH minus. And the question becomes, which wins? Which one produces more? And so to do this, we can compare our equilibrium values. And so remember that this K is equal to our concentration of our products divided by our concentration of our reactants. This means that the larger the K, the larger the equilibrium constant, the more products are produced. So, what we can do is we can compare our Ka and our Kb. And in this example, Ka is bigger than Kb, which means that there will be more H3O plus, the product from the Ka reaction, than OH minus, the product from the Kb reaction. And that means that this solution will be acidic, or is expected to be acidic. And so its pH should be less than 7. Okay, so on the next pages, I have this typed out neatly, so you don't have to try to read my handwriting. And I'm going to walk back over this and summarize this process again. Becomes, okay, so what I did was in my first step, I dissolved the salt into water and found the ions. In the second step, I looked at how the cation reacted with water, and I found that it is an acidic species with a Ka value. And in the, I keep doing that. In the third step, I look at how the formate ion reacts with water, and I find that it is a basic species, and I get this Kb value. Then in the fourth step, I put it all together. And so I find that my NH4 plus behaves as an acidic species with this Ka. I find that my formate behaves as a basic species with this Kb. And since Ka is greater than Kb, the solution will be acidic. This means that there is more H3O plus than OH minus. Okay, so on the next page, I'm going to walk through another example for you, and show you another example of how we work through these problems whenever we have two weak species in solution at the same time. As many, oops. Okay, so now I'm going to walk through another example. In this example, I have, do you expect a solution of methylamine carbonate to be acidic, basic, or neutral? So this is methylamine carbonate. And so my first step, like I've done before, is breaking the ionic species up into its ions. And so I get methylamine here, and I get the carbonate ion here. Now, I didn't balance this out. Notice how in this reaction there are two of these. That means that this 2 has to go out in front. So whenever the salt splits up into its ions, it breaks up into twice as many methylamine ions as it does carbonate ions. Now, this 2 is not going to affect anything in our steps. So, our second step is investigating how the cation reacts with water. And so I have methylamine plus water. And this is a weak acid. And so water is acting as the base, taking that proton, forming an equilibrium. This is a weak acid, which means that this reaction is described by a Ka, which we can find as the Kw divided by the Kb. And so my Kw is 1 times 10 to the minus 14. My Kb, I'm using my Ka, Kb table. My Kb is 4.4 times 10 to the minus 4th. And so I get a Ka value of 2.33 times 10 to the minus, Sorry about that. I get 2.27 times 10 to the minus 11. Step 3, I need to do the same thing with the anion. So I have CO3 2 minus plus water. This is an anion, so it's the base. Base takes the proton. Now, notice I'm only going to take one proton. This is a weak base, and the Kb is equal to Kw over Ka, which is 1 times 10 to the minus 14 divided by, now the Ka, I need to use Ka2 because carbonate is a diprotic species. So I need to make sure that I am using the correct Ka value. If you are confused about this, go look at the video where I explain how the Ka-Kb table works. And so Ka2 is 4.7 times 10 to the minus 11. And this gives me a Kb value of 2.13 times 10 to the minus 4. Step 4, I have to put it together. Wrong button. And so my KB is bigger than my Ka, which means that the solution will be basic. That means that my concentration of hydroxide at equilibrium is greater than my concentration of H3O plus at equilibrium. Okay, so like before, on the next slides, I have a summary of this typed up so you don't have to see my handwriting, and I will walk through it. Okay, so in the first step, I broke the salt up into its ions. I dissolved it in water. I then investigated how the cation interacted with water, and I found that it is an acidic species. It forms an equilibrium that is that of a weak acid with a Ka of 2.27 times 10 to the minus 11. And then I investigated how the anion reacts. Notice that I moved one proton. One proton moved. This is key. Any of these reactions, only one proton is going to happen at a time. And so I find that my carbonate is a basic species, and it has a Kb of 2.13 times 10 to the minus 4. Then, for my fourth step, I compare my Ka and my Kb, and I find that my Kb is greater than my Ka, and so the solution will be basic. Okay, I hope this is starting to make sense. In the next video, I will talk about what happens whenever you have an amphiprotic species, a species that is both acid and base. Remember, I have office hours, I'm answering emails, and I'm here to help with whatever you need. Have a good day.